Okay, permutation matrix. Suppose we have n objects, 1, 2, 3, all the way to n. Now a permutation is a map between the set S. You plug in. Now you need to make sure that the image P1, P2, Pn should be contains everything of this 1, 2, 3, n. Okay, so that shouldn't be two elements that has the same image. Okay, so this means it's a bijection, 1-to-1 map. And we give several examples of a bijection. And how do we write this in terms of a cycle notation? Okay, if we have a special permutation which switch only two objects, this is called a transpose. Okay, now if you think about it, any permutation, okay, you can achieve any permutation by just using transpose. Okay, suppose you want to arrange n objects 1, 2, 3 all the way to n in any order you want. What you do is you start with 1, 2, 3 all the way to n, and then you switch switch two at a time, switch two objects at a time. Then you can achieve any order. So this is what it says. Okay, now we want talk more about this permutation. Okay, this special permutation. Now let's see this. Suppose we're talking about n-dimensional vector space. So let E1 be this 1, 0, etc., 0. Now E2 is the second entry, the second component is 1, the other entries are all 0, etc. Then we have En, which is 0, 0, blah, blah, blah. The last one is 1. Okay. Now we choose this n basis to be the n objects. Okay. So we choose. So this is the n objects that we choose. Okay. So the set S is E1, E2, blah, 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 En. With n objects. Now we can use matrix to represent this permutation. Okay, permutation. For instance, if we want to switch EI with EG, okay, so we switch EI with EG. So switch EI with EG. Okay, IE, switch these two objects, EI with EG. IE, so we want a matrix P, want an n by n matrix. P. So it's Pij, subset, Pi, if you do the input of the vector Ei, then the output is Ej. If you input Ej, then you get Ei. If you plug in any other basis, if you plug in Ei, Ek, this will be Ek. For any key not equal to I and J. Okay. So this Pij will correspond to the transpose. Okay, Ij. Okay. Plug in I, you get J. Plug in J, you get I. Then plug in any other thing, you get it itself. Okay. So we have this picture. Okay, maybe let me write this backwards. So this transpose Ij, this we use Pij as a matrix. So for matrix, we can have matrix multiplication. Here we have multiplication of matrix. Of matrices. And here for transpose, for permutation, we can compose this permutation. Composition of per transpose. Okay, for any, so we get a permutation. You can get a permutation. So by compose this transpose, and then we can get any permutation. And here we can get permutation matrices. Permutation matrices. Okay. Okay, for instance, let's do now what this PIJ looks like. PIJ looks like this. As matrix PIJ is this thing, if you can check. So if we have n by n matrix, and then this is the ice rule. Sorry, it's ice column ij. And here you have I, and here you have J. Okay, so this will be, this point will be, this intersection will be I through J column. Okay, so this is I through J column. This column. Okay, now on the diagonal, we choose this thing to be 1, 1, 1. And this is on the I and J, we get 0 and 0. But here on the IJ, we get here, we get here, we get 1. Then all others is 1. Then on the diagonal, it's 1. Okay, on the off diagonals, everything is 0. Okay, so this is, you can check. This is the transpose. You can check, use the coordinate form. So this is the matrix representation of.
Let me be laptop.
This is the matrix representation of this transpose. Okay, this is the matrix representation of the transpose. Now permutation, how many permutations are there? If you think about it, use some combinatorics. Any order for n objects, 1, 2, 3, 4, all the way to n. You can check. There are n choice for the first object. And then once you fix the first object, then the next object you have n minus 1 choice. And then etc. n minus 2. Then the last object you have no choice to put everything in a line. Okay. Okay, so this is actually, this is the total number of permutations. So this is actually n factorial by definition. So this we get, there are exactly n factorial permutations. N factorial permutations. Okay, now let's see some example. P to be this permutation, 1, 2, 3. What does this P? What this P does is we map it. 1 goes to 2, and 2 goes to 3, and then 3 goes to 1. So E1 under P goes to E2. E2 under P goes to E3. E3 goes to E1 under P. Okay. So this will be, now the image of E1 is E2, which is 0, 1, 0, 1. E3 is 0, 0, 1. E1 is 1, 0, 0. Okay. Now the image of E1, E2, E3 gives us the columns. Okay, gives us a column. The image of E1 gives us the first column. Image of E2 gives us the second column, and the image of E3 gives us the third column. So P, this P. The matrix representation of P, the matrix representation of P, it should be the first column image of E1, E2, which is 0, 1, 0. Now the second column image of E2, it should be E3, 0, 0, 1. And E3 has image E1, which is 1, 0, 0. Okay, so you can check this. What this matrix P does is exactly the permutation 1, 2, 3. Okay, now this example, P is this transpose, P is 1, 2. This means E1, 1 goes to 2, 2 goes to, then 2 goes to 1, okay? This means E1 goes to E2, E2 goes to E1. Now E3 is fixed, E3 goes to E3, okay? So E2 will be 0, 1, 0, E1 will be 1, 0, 0, E3 is 0, 0, 1. So you write down each column according to the image of E1, E2, E3. So you get a P correspond to the matrix representation of P is 0, 1, 0. The first column is image of E1. The second column is image of E2. Third column is image of E3. Okay, so this what this P does is this transpose 1, 2. Okay. Now, if we study, remember when we study objects, like a permutation, we do not study one object, okay? We do not study one object, it's because it's boring. We study an object by its relation with other objects. So when we study permutation, we study all possible of permutations. So if we have n objects, then all permutations of these n objects, all permutations of n objects. First of all, it's invertible. Any permutation is invertible, i.e., if you arrange 13 order of objects 1, 2, 3, all the way to n, you can recover the initial order. Okay, you can recover the initial order by backwards operation. So it's invertible. So of course, the permutation matrix is also invertible. Okay, now invertible thing is actually tells us certain symmetry of objects. Okay, certain symmetry of objects. So symmetry, one of the most important tools to study symmetry is actually one object called group. Okay, any object forms a group. Now the idea of group is really, really important. Okay, for instance, for permutation, you can compose a permutation with another permutation, so you get another permutation, which is again permutation. Okay, now for anything you can invert it. You can invert it. So this actually, this group, this object, the collection of all permutations on any objects is called the symmetric group. Symmetric group on n letters with notation Sn. Okay. Now this is the symmetric group in n letters is one of the most important objects studied in group theory. Today, most of this important property of this symmetric groups is already known. Okay, well studied for these objects in group theory. Now, if you study a higher course after linear algebra, which is called representations of groups, representation theory of groups. Actually, you use matrix to study symmetry of objects. You will actually have a chance to study this this object, the symmetric group in letters. Okay, it's a really beautiful subject. Okay, now for permutation, we use matrix representation of a permutation. We have certain property for permutation matrix. Okay, theorem. Now for a permutation matrix, the inverse equal to the transpose. Here the word transpose is has two meaning: transpose of a matrix and a transpose as permutation. Switch to objects. Okay, don't confuse. If P is a permutation matrix, permutation matrix. Then P inverse equal to P transpose. Okay, transpose. We switch the row with column. Okay, proof. Now, of course, if we have a transpose, remember, you see, if we have a transpose, the transpose is we flip. You see, we switch IJ. So this is symmetric. If we have a transpose of matrix, then for a transpose, the inverse is exactly with agree with P transpose. Okay, because for transpose, if we do transpose twice, okay, switch 1 with 2 and then switch 2 with 1, then do it twice, then this does nothing. So identity, everything is fixed. And then we can achieve P, any permutation as a product of a transpose. So we can achieve permutation as a combination of a transpose. Think about it, okay? So you can write P as a product of transpose. Think about it. Any permutation, you can achieve that by switching 2 objects at one time and then compose, until you achieve your desired order. So P, we can write as, for instance, let's do Q1, Q2, etc., etc. Then we do the last transpose, it's Qn. Now for transpose where Q1, Q2, etc., Qn is order 2 permutation, i.e. Is a transpose. Transpose, i.e. Qi only switch 2 objects at one time. So of course, Qi squared, okay? If you switch 1 with 2, then do it again. Switch 1 with 2, then you get a 1, just switch to 1, 2, switch with 2, nothing changes. So identity, okay? So this, if we do it twice for transpose, this will be the identity, nothing is changed. I equal to 1, 2, 3, all the way to n, okay? Then you see P inverse. P inverse. Now when you do inverse, you need to be careful. This inverse. So this will be, you need to flip the order. So this will be Q1 inverse, Q2 inverse, and then Qn inverse. You can multiply P and with this P inverse and use association law to show that this is exactly identity. Okay, this is exactly identity. And then here we have Q I inverse equal to Qi. And this is also equal to Qi transpose. Okay, so this we get Q1 inverse is Q1 transpose. Q2 inverse is Q2 transpose. Qn inverse is Qn transpose. And then remember, for transpose, product of transpose, we need to switch the order backwards, okay? So we get a Qn times Q1, Qn minus 1, Q2 times Q1 transpose. Okay, we use the fact that A times B transpose equal to B transpose A transpose. Now, if you have this property for 2, for the product of 2, then you can apply this recursively to get this property for n objects, product of n matrices. Okay. So this is actually equal to exactly this is P transpose. Then we're done. So we get P inverse is exactly P transpose. Then we are done. Okay. So for permutation matrix, its inverse agree with the transpose. Okay, let's see some example of a permutation, how we apply permutation. on matrix, to do operations on matrix. Remember, this is kind of elementary matrix. We use elementary matrix to do rule operations. Remember, we have 3 rule operations: switch 2 rules, then multiply a rule by a scalar, non-zero scalar, and we also have add a multiple of a rule to another rule. Okay, these 3 operations, rule operations, can be achieved by elementary matrix. Now we use permutation matrix to do elementary operations on matrices. Okay, suppose we have this A. Let's see this example. Let's see this example. Suppose A is this matrix. We want this makes this A to be upper triangular. So this is not upper triangular. So the question is, which permutation that we need to do? P, which permutation P makes this PA, makes PA upper triangular. Upper triangular. Now you see, how do we make A upper triangular? Well, you see, if we put rule 1, so this is rule 1, this is rule 2, rule 3. Now rule 2 is 1, 2, 3, has every element, non-zero element. So we put rule 1, so what we do is, we put rule 1 as rule 2, we put rule 2 to be rule 1. And then we put rule 1 as rule 3. And then rule 3 to be rule 2. And then if we do this operation, switch these rules, then what we get is now 1, 2, 3. And then the second rule is this. The second rule is 1, 0, 4, 5. And then the third rule is 0, 0, 6. Okay? So you see, this is upper triangular, upper triangular. So what this matrix does is, you see, rule 1 maps to rule 2. So it's 2 goes to 1. Then 1 goes to 3. And then you see it's 3 goes to 2. 3 goes to 2. Okay, so what we get is, okay, so if you write this basis, E1 goes to 1 goes to 3 will goes to E3. Okay, now E2 will goes to E1, E2 will go to E1. Now E3 will go to E2. So E3 is 0, 0, 1. E1 will be 1, 0, 0. E2 will be 0, 1, 0. Okay. So according to the image, okay, E1, E2, E3, this gives us the column of this permutation. Okay, column of this permutation. So P should be the first column, image of E1, 0, 0, 1. Image of E2 is the second column, which is in this case, with the second column, 1, 0, 0. Third column is given by this, which is 0, 1, 0. Okay, now this is this column, 0, 0, 1. So we can check P. If we have a P, then PA is 0, 0, 1, 1, 0, 0, 0, 1, 0. Then multiply A, which is 0, 1, 0, 0, 2, 4, 6, 3, 5. Now what do you get? Using what do you get is the first root times the first root times the first column. You get 1. The first root times the second column, 0, 1, 0 multiply 0, 2, 4. Okay, second column. Okay, the second column. Okay, the second column 0, 2, 4. multiply multiply 0, 1, 0, 1, 0. So you got a 2 here. The first rule 0, 1, 0 multiply the third. You get this is 3. Now the second rule multiply the first column. You get a 0. Okay. So second column. So we using second column 0, 0, 1. Multiply the first rule, first column. Then you got a 0. Multiply the second column. Then you got a 4. Multiply the third column. You got a 5. Okay. Now we use the third. Use the third rule. Let's see a color. Okay. By using the third rule, 0, 1, 0. Sorry. 1, 0, 0. Multiply. If you multiply the first column, then what you get is here you get a 0. Multiply the second column, then you get 0. Multiply the third column, you actually get the first entry, which is 6. Okay. So this is exactly upper triangular. So you see, we can achieve rule operations use permutation matrix. Okay. Okay. Now we multiply a matrix from the left. Okay, from left, PA. Now, of course, if we do left thing, multiplication on left will permute the rules. If we multiply on the right, then we will permute the columns. Okay, so this is an important thing, key idea. Multiplication on left by a permutation. Permutation matrix. On the left. Permute left of a matrix. On the left of a matrix A. Matrix A permutes the rules of A. Now, if you use symmetry, then multiplication by permutation. So multiplication 1, 2, multiplication by a permutation matrix on the right, okay, on the right of a matrix A permutes the, now left you go to right, and then rule by symmetry you get columns, okay, columns of A, okay. So if we rules, then on the left, then permute the rules. Now on the right, it will permute the columns. Okay. Okay, let's see some example. How do we use permutation matrix to get what we upper triangular form? Let's see lower triangular. Let's see. Suppose we have this. Suppose we have this. A is again this matrix as what we did in the last example. Suppose this matrix A is exactly 0, 0, 6, 1, 2, 3, 0, 4, 5. Now we want this thing to be lower triangular. What does lower triangular mean? Lower triangular means so above the diagonal, everything here is 0. So it's lower triangular. So every non-zero entry should be lies below the main diagonal. Then it's lower triangular. So on the upper side, of the main diagonal, every entry is 0. Every entry is 0. Okay. So what we do is, you see, how do we do that? We do column operations. Column operations. Remember, column operations, we should multiply the matrix from the right. Multiply the matrix on the right. Okay, multiply the matrix by a permutation matrix by on the right. So here we first, so this is the, we do column operations. So this is C1, C2, C3. So we need to move the zeros to the right side of a matrix. Okay, right up side, right up corner of this matrix. Okay, so you see we have this, the first rule of matrix A 0, 0, 6. We should move these zeros to the right. Okay, move the zeros to the right. So you see what we do is we switch. How do we move the 0 to the right? Well, we switch the columns. Column C1 permute with C3. Okay, permute this. So C1 switch with C3. Column C1 switch with column C3. So what we get is, in this thing, we get column switch. So 6, 3, 5. Now the second column is fixed. Now the third column is the first column, 0, 1, 0. Okay? Then what we do is we flip, do rule operations. So this is R1, R2, R3. So we switch R1 with R3. So this can be achieved by permutation. Okay? Now we do rule operations. So this time when we do rule operations, we multiply the permutation matrix on the left. Then we get switch rule 1 with, so rule 1 is fixed. Rule 2 switch with rule 3. So we get a 5, 4, 0, and then 3, 2, 1. You see here, so it's upper, so it's a lower triangular. All zeros are above the main diagonal. Okay, all zeros, all 0 entries are all above the diagonal. Okay, so this is lower triangular. So we are done. We're done. Now let's see what multiplication, what matrix multiplication that we should use. So from the matrix A, we first do column operations. Remember, column operation, what should we do? Column operations, we should switch, multiply on the right, switch 1 with 3. And then we do rule operations. Rule operation, we should do multiplication on the left. Okay, we switch 2 with 3. So it's permutation 2, 3. Okay, where you see P13. What does P13 does? P13 is E1 goes to E3. Okay, E3 goes to E1. E2 goes to E2. E3 goes to E1. So you can write P3. You can write P3 as P13 as, now E1 is E3. The image E1 is E3, which is 0, 0, 1. The image of E2 is E2. It is 0, 1, 0. Image of E3 is E1, which is 1, 0, 0. Okay. So this is P13. So it's switched 1 with 3. Now P2. P23 is, you see what P23 does is E1 goes to E1. E2 goes to E3. And E3 goes to E2. Okay, if you write down what P23 is, now E1 is E1, 1, 0, 0. E2 goes to E3, which is 0, 0, 1. E3 goes to E2, which is 0, 1, 0. Now you check this YR matrix multiplication. Check P23 times A times P13 is exactly equal to the matrix, that we get. Check that. Okay, check that. We will not check this this is straightforward multiplication. Once you work out, you'll find this actually exactly this action. Okay, exactly equal. Okay, homework for this section. Homework for this section. 2.7. Let's do number 5, number 12, number 32. Okay. Okay, all right, now let's start another chapter. Chapter 3. Okay. Chapter 3. Vector spaces and subspaces. We already seen several examples of vector spaces and subspaces. Now we actually gives definition of a vector space. Okay. Now a vector space is a collection of vectors that it's not just a collection of all vectors, but we have certain relations between these vectors. Okay. Okay. So let's start with this vector space V, which is xi plus yj. Now x, y, they are real numbers. Okay, so this V is a set collection of vectors. Is a space of vectors, two-dimensional vectors of vectors on the xy plane. Now for this vectors, okay, we have, so it corresponds to the point x0. Okay, now you see actually V, this is in R2. Now we have a correspondence, okay, of the vector space with this R2, okay, pairs of real numbers. Okay, we have the natural addition for vectors. Okay, then we define, if we let U be AI plus BJ. Which is coordinate form AB. And we have V to be, let's see, is to be CD, CI plus DJ, which is CD. Okay, then we have vector addition. This is AB plus CD. Now we have a natural definition. A plus C, B plus D. We also have scalar multiplication. Lambda V, let's use lambda U. Lambda U, which is lambda AB, which is lambda A, lambda B. Okay. Okay, now the collection of vectors that together with the relation operations on vectors, scalar multiplication and the vector addition, then we call it a vector space. Okay, a vector space is not just vectors. It's not just vectors. It's including the relation between vectors. That is important. Okay, that's important. Okay, then it's trivial to check. Now, if we have a collection of vectors that satisfies similar properties, then it forms a vector space. So it's trivial to check. Trivial to check the operations. 1, u plus v commutative. Now associative of addition. And we have scalar multiplication. Association law with scalar multiplication. Distribution law for scalar multiplication. Okay, then zero vectors. Zero vectors. Uniqueness of zero vector. Zero vector. So there exists unique zero vector. Such that u plus 0 equals u again. And then we have 6. 1 times x equals x. And 7, u plus negative u is 0. And 8, c, constant c, let's use lambda. Lambda x, lambda uv is lambda u plus lambda v. Okay, now of course, you may ask, why do you list all these properties? It seems really boring to have these kind of properties. The thing is, we do have intuitive definition of vectors in terms of, R2, R3. We have this kind of specific geometric vectors. Now, this geometry, sometimes, geometry is intuitive, but mathematics is based on logic. There are certain examples that may be not so intuitive. Then actually we need to check this kind of axioms of vectors, vector space. And it's, on the other hand, if you have a set of axioms, this is actually a really good thing for mathematics. If you study geometry, we have the Euclidean geometry, which dominated for many times, that people believe that there shouldn't be other models of geometry. This is because that the fifth axioms, the parallel axioms, that people believe the fifth axioms is truth, okay? However, people find that we cannot prove the fifth axioms, the parallel axiom, which means means it's independent of other axioms. Then people modify the fifth axioms by other axioms, and then people get other model of geometry, non-Euclidean geometry. This actually tells us sometimes our intuition can, prevent us to find some new thing. So we should, intuition is good, but we should also, on the other hand, try to use logic as a complement of intuition. Okay, so this is why we use these axioms. Okay, use this axiom to write down the axiom of vector space. Now, if you know the development of mathematics, there are different kind of traditions. There are different kind of mathematicians. You know, mathematicians, they are all human beings. Different kind of human beings have different personality. And there are different kind of schools in, you know, for mathematicians. You know, one specific mathematician is from German school, David Hilbert. David Hilbert tried to write down the foundation of mathematics, use logic, okay, based on logic, formal logic. So this is actually the logical, use logical thing, write down everything in logic is, you know, has a tradition in German. The other kind of mathematician, like Poincaré, the father of topology, you know, is more geometric, use geometry intuition. He is actually another kind of mathematician that relies on heavily on intuition, okay, intuition. And today, there are also, you know, some people relies on intuition, like some geometer, and some other mathematician prefer logic. So that's still, you know, this kind of different style between intuition, geometry, and formal logic. Okay, today this, you know, argument still exists in mathematics. Okay, then it's maybe too far. Let's go back to the definition of matrix of a vector space. Now, a vector space definition. So this partially explains why we should do this thing. Why it looks boring, but it's still necessary. Okay, sometimes. Okay, a vector space V is a set of vectors together with rules of vector addition and scalar multiplication. Vector addition and multiplication, scalar multiplication. That satisfies axiom 1 all the way to 8. 1 to 8. Okay, that satisfies 1 to 8. Okay. Okay, let's see some examples of a vector space. Example, a matrix, let M be the set of 2 by 2 real matrices. Okay, the set of 2 by 2 matrices, real matrices. Okay, then it's this. So M is this thing. A, B, C, D. A, B, C, D. In R. By the way, now you see we don't do, you know, when we do geometry, you know, X, Y vector on 3-dimensional space, we define inner product. You see, in the vector space, we do not require a structure of inner product. Okay, inner product tells us the length. Okay, inner product tells us the length of a vector. Now you can actually have different kind of a measurement for the length. Okay, even for the same vector space, even for the same space, you may have different measurement for metric. Okay, length. Okay, So inner product is not essential to a vector space, okay? Because even for the same vector space, you can equip different structure of inner product. So inner product is not necessary for a vector space. You need to be careful, okay? Okay, now here we have ABCD four real numbers. So we can view this as, so you can view it as R4. For instance, U0, 1, 0, 0, this is basis. This corresponds to 1, 0, 0. So it's just a different manner to write down things, okay? It's just different way to write component. This is a different way of writing component. So this third component, and this is the fourth component. Of course, this is just my own choice, and you can use your own choice to get this, relation. So essentially, so we get as vector space, the 2 by 2, the set of 2 by 2 real matrices is nothing else. It's the same thing as the R4, the four-dimensional real space. Okay, so we have, so we don't use the word equal. Okay, we don't use the word equal. We use, this is called this. We use this thing, isomorphic. This word means equal. We often use equal for numbers. 2 equal to 2, x equals x for numbers. And then for vector space, we not just have the structure. We don't have. We have both objects. Okay, objects. We should get a correspondence between objects. And also we have the structure of addition and multiplication, scalar multiplication. And this thing, this equal, should also include this kind of operations, okay? Equal of operations, this operations. So this relation should also respect the scalar multiplication and the vector addition, okay? Vector addition. You can easily check this rule, okay? Easily check this rule. For instance, matrix scalar multiplication, ABCD, we multiply to each component. So this, you can check this rule, the above rule, the above rule, respect this scalar multiplication. And this above also respect to the addition, vector addition. So they are the same vector space. So we see isomorphic. Isomorphic has more meaning, because we should check at the level of object, and also we should check at the level of operations, scalar addition, scalar multiplication and vector addition. Although this is obvious. B2 here. Okay. All other properties can be easily checked. Okay. All other properties can be easily checked. So this actually shows that the set of 2 by 2 matrices is a vector space that looks like R4. It's the same thing as R4. So this shows that M is a vector space, isomorphic to R4. Isomorphic. Okay. Other example. So this has finite dimensional vector. Okay, this is a vector of dimension 4. Okay, sometimes we can get infinite dimensional vector space, okay? Infinite dimensional vector space. So this example, CR is the set of f R to R, f is continuous. So it's a function from R to R. So it's continuous function from R to R, defined everywhere. Okay, so this is actually, we can equip a vector space structure on CR, okay? So CR is a set of object, real continuous functions. We can equip the vector space structure to define vector addition and scalar multiplication, okay? So if we have two continuous functions, we can add them. So we have the obvious thing. So f plus g. So we just f plus g as a function. This is equal to fx plus gx. Okay, and then scalar multiplication, scalar f at x, we assume it's a scalar of fx. Okay, so this check other properties you can easily check. Okay, you can check axiom 1 to 8. Okay, this is actually easily checked. Okay, so 1 to 8 property can be easily checked. So this shows that this continuous function is a vector space. Okay, the set of continuous functions from R to R is a vector space. So it's actually infinite dimensional. It's a vector space. Okay. Now maybe another example. Polynomial of degree less than n. Okay. Pn, let's see this Pn to be this. Pn to be this collection of polynomials that has degree less than n. Okay, here x is a variable, ai is in R is from 0 all the way to n. So the coefficients can be 0. Okay, can be 0. Okay, so now we can have a vector space on this set. Okay, so P consists of polynomials with degree, real coefficients, degree less than n, real coefficients, real polynomials of degree less than equal to n. Now, for instance, if we have fx, which is a0, a1x, blah, 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 plus anxn. Okay, whatever this coefficient is. So it corresponds to a vector. So we have n plus 1 numbers. So we have n plus 1 numbers. So now gx, which is b0 plus b0 b1 x plus etc plus bn xn, it corresponds to this b0 b1 dot 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 bn. This again in vector space of Rn plus 1. So you can check that. So this is actually v1. Let's see, this is v2. So f correspond to v1, g correspond to v2. Now f plus g, which is a0 plus b0 plus a1 plus b1 x, blah 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 blah, plus an plus bn. Combine similar terms, then this corresponds to this vector, a0 plus b0, a1 plus b1, etc etc. plus an plus bn. This corresponds to use vector addition. This is exactly v1 plus v2. Okay. Now v1 is the vector a0, a1, etc. an. V2 is exactly b0, b1, bn, etc. Okay. So this correspondence. Of course, you can check scalar multiplication. Scalar multiplication fx is you distribute to every term. Distribute to every term. So this corresponds to lambda a0, lambda a1, lambda an, which is exactly lambda a0, an, which corresponds to lambda v1. Okay, so you can check this. Actually, we have a correspondence. Okay, this is actually Rn plus 1. We have this correspondence. Vector polynomial of degree less than n, less than or equal to n, is isomorphic with Rn plus 1. Okay. Now, of course, we can define polynomial of any degree. So you see, P1 is contained in P2. Okay, because P2 contains polynomial of degree 2, but P1 doesn't. So we can go higher and higher. P2 is contained in P3, P3 is contained in P4. So we can get higher and higher polynomials, etc., etc. So we let P polynomial functions to be the union of all the P, n from 1 to infinity, is the collection of all polynomial functions, is the set of all polynomial functions. All polynomial functions. Remember, polynomial functions are continuous. So P is a vector space. So of course, P is a vector space. You can easily check. Now, since polynomial functions are continuous, P is contained in, since polynomial functions are continuous. Polynomial functions are continuous. We see we have P is contained in continuous functions. So we have P is contained in CR. So this containment is as a set. Now, as vector space, they have the same vector space structure, i.e., the vector space structure of P can be extended to the vector structure on CR. Okay. So P is contained in CR. Okay. So you see, P is a subspace of CR. Actually, we have the following. We have the following theorem, which gives us a relation between polynomial functions and continuous functions, which says the famous Stone and Weierstrass theorem. If you do study analysis, you will have a chance to study this theorem in details. Weierstrass theorem, which says continuous function on a bounded interval, closed interval, can be approximated uniformly by polynomial functions. Okay, every continuous function defined on a closed interval, bounded closed interval. A to B can be uniformly approximated. Now this uniformly means you can control the error term everywhere. Which is universal for the location as close as desired by a polynomial function. I.e., we can approximate a continuous function on a bounded continuous interval. Okay, bounded continuous interval. And you can control the error term. Okay, now the error term is, you can make sure the error term is less than any epsilon everywhere on this interval A to B. Okay, maybe give you one example. Let's see sine x on let's see bounded interval negative pi, just one period of sine x pi. So we can find a polynomial representation, polynomial approximation of sine x. Now a natural choice, for instance, there are many choices. You can use any polynomial, Taylor polynomial at any point within this zero, within negative pi to pi. Now we just use the Taylor polynomial at 0. So we get the Maclaurin for sine x. You know, sine x, which is the Maclaurin polynomial, which is the first term is x, the next term is x cubed over 3 factorial plus 5 factorial x, you know, to the 5 minus x power 7 over 7 factorial, etc., etc. I.e., you can use polynomials. You can use polynomials to approximate the thing. Okay, if you use higher degree, you can get better and better approximation. Okay, so the error term can be arbitrarily small. Okay, whatever point within this negative pi to pi. Okay, so you get a better and better approximation if you let the polynomial go higher and higher degree. Okay, homework for this section. 3.1. Number 20, number 22, number 23, number 26, number 32. Okay, let's continue new sections. Okay. Let's see this example. Let's go to the next section. 3.2. The nullspace of a matrix. Okay. Now let A be a matrix. Be an M cross N, M by N matrix, i.e., we have M rows and N columns. So A to be this. So we have this. We have M rows. If we write as root vectors, it's R1, R2, Rm. We have M root vectors. And then for each root vector, I through, we can write it as AI1, AI2, dot, dot, dot. Now we have n column, AIN. Okay, so we have n columns, n columns. Okay, we want to find the row space and the column space. Okay, so I is from 1 to all the way to m. Now, if we have, so this is the A is mn. Now, A should X on vectors, so if we let X be X1, X2, dot, 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 Xn, transpose. So this is column vectors in Rn. So X is in, X is Ny. So it's a column vector. We did a transpose, so it's a row vector becomes column vector. So E is Ln, and then X is Ny. X is Ny. So we can multiply them. So we get M1. Okay. So okay, then definition. The null space is the null space of a matrix A. Let's see, an Ln matrix A is defined as null space of A, so it's a vector space. X in Rn such that Ax we get a 0. Okay. So this is, you should compare this is we input X to the machine A, then we get a 0. 0 here, 0 means 0 vector. Okay. I.e. what input that we input to the machine, that we get a 0. Okay. So you should compare this with 0 of a function. Okay. 0 of a function. There another name. You can also say somewhere this is called kernel of a matrix A. This is the same thing. The null space is the same thing as the kernel. It's also called a kernel of A. Now, it can be checked that null space of A is a vector space. It can be checked. Null space of the null space of A is a vector space. Of a matrix A is a vector space. Is a vector space. Now it can be easily checked if A check if X, Y is in the null space. For instance, let's just easily check. Then this means Ax is 0, Ay is 0. Now the product of A with X plus Y use linear properties. This is Ax plus Ay distribution. This is 0 plus 0 as vector. This we get a 0 vector. So this means X plus Y is again in the null space NA. Okay. Now if you do scalar multiplication, lambda X, you let Ax on this thing, and then by linear property you can factor out lambda out. So it's lambda Ax. which is lambda times 0 vector, which is again 0 vector. So which means lambda x is in the space null of A, null space of A. Okay. So other properties of a vector space you can easily check from the property 1 to 8. Okay. So we assume that this is a vector space. Okay, it's a vector space. Now to tell this vector where this vector space is, we need to find some key important information for this vector space. For instance, what dimension of this vector space, and if you know the dimension, if we know the dimension, can we find a basis? Okay, find a basis of this space, i.e., a set of vectors that generate the minimum set of generators that span this vector space. Okay. Now we use the column picture to do this. Column picture to do this. Now, okay. So use the rule picture. It says if x is so rule picture. We can use either rule picture or column picture. Rule picture says x is in the null space of A if only if x is perpendicular to the root vectors of A. Okay, so this means by definition by definition this means A times x is 0. Now if you use column vectors, this means R1 times a dot product with x is 0, R2 dot product with x is 0, dot dot dot. So this means Rm dot product with x is 0. Okay. So this means x is perpendicular to every root vectors. Perpendicular to all root vectors of A. Okay, which means x is perpendicular to the vector space spanned by the root vectors, to the space, vector space spanned by all root vectors. Okay, let's see some example. Let's see this example. Let's see this matrix. Let's see, choose this matrix A to be this 1, 1, 0, 0, 1, 1, 1, 2, 1. Okay. Okay, we need to find these root vectors. Find the null space of the matrix A. Okay, let's look at the root vectors. So 3 root vectors. So the first root 1, root 2, root 3. Okay, root 1 is 1, 1, 0. Root 1. Root 2 is so the root 1 is I plus j. K is 0. Now root 2 is 0, 1, 1. It's a root 2, which is j plus k. Now root 3 is actually, if you observe, root 3 is exactly equal to root 1 plus root 2. Root 3 is root 1 plus root 2. So they are not linearly independent. So root 1, root 2, these actually they are linearly independent. So they span a plane. So if we plot this geometrically. So what is root 1 corresponds to root 2? Okay, let's plot the thing. X, Y, Z. Z. Now, let's plot this vector. So this we have O. Okay. Okay, suppose we have a unit cube. Okay, so let's see, this is the O here, A, B, C, D, E, F. Okay. Okay, you see the coordinate. Then you see R1. R1 is I plus J. It's 1, 1, 0, 1, 1, 0. So you see this will be OB. Okay, OB, you see OB. OB is actually OB equal to I plus J. Okay, B has the 1, 1, 0. Okay, the height of B is on the floor, so it's a 0. Okay, so XY coordinate is 1, 1 for B. So you can check B is 1, 1. Okay, 1, 1, 0. So what is another root vector? Root vector, the second root vector is R2 is J plus K. Actually, it equal to so it's 0, 1, 1. So X is 0, so it's on the YZ plane. On the YZ plane, it's 1, 1 on the YZ plane, so it's actually equal to OD. Look at the coordinate of D. Look at the coordinate of D. Look at the coordinate of D. So D is actually 0, 1, 1. Okay. Then you see what's the rule space? What's the space spanned by the rule vectors? So rule vectors span the plane. Okay. We have two linearly independent vectors, so they span a plane. So the rule vectors. Now rule 3 is not independent with rule 1 and rule 2. So we just use rule 1 and rule 2. So the rule vectors span the plane OBD, ODB. Okay, the plane OBD. So the rule space is OBD. Okay, now from the geometry, you see from the geometry, we need a vector space that is perpendicular to the plane. Okay, also as vector space, it is sort of one-dimensional vector space, it should pass through the origin. You see? What is a vector space that is perpendicular to this plane in R3? Okay, so the null space in this case, which is a line that a vector space that is perpendicular to this plane. In this case, actually we have a choice. If you look at the picture, the diagonal of this cube, CF, the diagonal of the CF, if you know geometry, this actually you actually know that CF is perpendicular to the plane, to this plane, OBD. So CF, find the coordinate of CF. Find the coordinate of C and F. The coordinate of C, what is the coordinate of C and the coordinate of F? Can anyone tell me what's the coordinate of C? What is the coordinate of F? What is the coordinate of C? Question?
0, 1, 0.
C is 0, 1, 0. What is F? What is F?
101.
101. Good. Okay, then you see CF. Head minus 2, so it's y, negative y, y. Okay. Now you see, let's check. Let's check whether CF is perpendicular to the R1 or perpendicular to the R2 or not. Okay. So CF dot product with R1. R1 is OB. Okay, OB, which is y, negative y, 1. Dot product with y, y, 0. So what do we get is, you see, we get a 1 times y plus negative 1 times y. So we get negative y plus 1 times 0, we get a 0. So this is actually 0. So actually we get a CF is perpendicular to OB. Now similarly, we do CF times R2. R2 we know is OD. It's a y, negative y, 1 times OD is 0, 1, 1. The first product we get a 0. Next one we get a negative y. Last we get a y. So this is actually 0. So we actually know CF is perpendicular to OD. So the null space is exactly the line that are parallel to CF. Remember, a vector space, to include the 0 vector, we should assume that the vector space, the line should pass through the origin O. Okay. So the null space, the null space of A, null space of A is the line parallel to CF, pass through origin. So it's lambda CF. You know, lambda is real number. Okay, multiple of the vector CF. So if you write down coordinate form CF, we already have CF, the coordinate of CF. Okay, it's 1, negative 1, 1. So multiply lambda, everything multiply lambda. So it's a lambda, negative lambda, and lambda. Okay, where lambda is in R. So this is actually the vector space. So this is the null space of A. So in this case, you see null space is dimensional 1 dimensional, and the rule vectors span a plane which is 2 dimensional. Okay, so you see this matrix is 3 by 3. You see in this case, the rule vectors lies in 3 dimensional space. They span a 2 dimensional subspace. And then the orthogonal part is 1 dimensional, which is 1 dimensional. So you see we have 1 plus 2 is 3. Okay, so this is dimension of null space. And this is dimension of root space. Hold on. So it's a dimension of the vector space spanned by root vectors. Let's just see it. Let's call it a root space. Okay, dimension of root space. Vector space spanned by root vectors. Okay, and then this 3 is dimension of the vector space. Dimension of the space that the root vectors lies in. Okay, so actually this is you see this is exactly number of rules. Sorry, it's get confused. So this should be the number of columns of A, number of columns of A. Okay. Okay, let's see another example. let's see, E is this thing. E is this matrix. 1, 2, 3. Okay. So column number, it has 3 columns, 1 row, 1 row. So it has 1 row. 3 columns. So the column number is 3. Now EX, so it's 1, 3. Now we should let X be 3. Okay, 3, 1. Okay, EX is equal to 0. EX equal to 0 as vector. So it should be X is to be, so it's A, X should be 3, 1, 3, 1. So X, suppose X is, let's see, it's XYZ. XYZ. So EX, you see, this case we have dot product. EX, in this case, we get root times column. So we get a X plus 2Y plus 3Z. Okay. So we get the thing to be 0. So this actually defines a plane. This defines a plane. So all possible solution x, y that satisfy this equation is a plane. The above equation, this above equation defines a plane. Defines a plane. So the null space, what is the null space? The null space is a plane. The plane is through 0. Defines a plane with normal vector. Normal vector n to be 1, 2, 3. Okay, then the null space is, okay, if we plot a vector 1, 2, 3. Okay, X is 1. Okay, 1, 2, 3. Okay, let's do it. Z is 3. Okay, if you this is the normal vector. It should be, we cannot see it. It should be this direction, normal vector. Okay. Now if we plot here, okay. So the normal vector, this is A, O, B, C, D, E, F. So the normal vector, this is G, or normal vector is OG. Normal vector is OG. Now, what's the null space? The null space is a plane that are perpendicular to OG and pass through O. So it should be, looks like if you plot it, it should be some point through O, a plane through O. It's not a very if you plot it, somehow you need to make sure it's perpendicular to this plane. Okay, perpendicular to OG. Okay, perpendicular to OG. Okay, then you see what's the dimension of the null space? Because it's a plane, so it's the dimension of the null space 2. Now the column, the root vector is 1. Okay, root vector is 1. Root vector spine is the dimension of the root vector is 1. So the root vector is rank of A is 1. Remember, we define rank of A. We can define rank A as the dimension of the column space or the dimension of the root space. They are actually the same rank. They're the same. Now the column number. How many columns? Column number of A. What's the column number of A? Column A has 3 columns. So column number of columns of A is 3. You see, dimension of null space plus the dimension of the root vector space rank A is, now in this case, is 2 plus 1 is 3, equal to the column number. Okay, equals to the column number of A. Okay, let's see more examples. A is this 1 1 0 0 0, everything is 0. Okay, the root space. So root 1, you see root 1, root 2, root 3. Root 1 is 1 0 0. Root 2 is 0 1 0. So this root 1 is I, root 2 is J. So root 3 is 0. So 0 vector. So the root space is spanned by I and J. I and J. This span I and J span the XY plane. So the root space is the vector space spanned by I and J, which is the XY plane. XY plane. Okay. Now, what's the null space? What's the null space? You can check AXY. AXY. What you get is XY0. Okay. To make sure the product is 0, so AX is 0 if X equals XY. XYZ. Then this means we should get XYZ, XY0, which is AX to be 0 0. So this implies X should be 0, Y should be 0. Okay. So this Z can be anything. Z is free. Z can be anything. Z is free. There's no restriction on Z. So X, so this is, so null space is 0 0 Z, which is Z is in R, all real numbers. So null space. So null space of A is the thing. I should write it as column vectors. So 0 0 Z, 0 0 Z. Now this is actually, you see, this is exactly the Z axis. This is Z axis. Z axis. Okay, Z axis. Now, which is the line? Okay, you see, again, the root space is XY plane, has dimension 2, i.e. rank A, dimension of the root space is 2. Then null space, dimension of the null space, dimension of a line, Z axis is 1. So you see rank A plus null A is exactly the column number of columns of A. In this case, we have a 3. Okay. Okay. How do we get the rank? How do we get a rank? How do we find the dimension of the root vectors? Now we actually use elimination. How do we find a rank of a matrix? Let's see this example. Rank of matrix. we do this example. Let's see A to be this. 1, 2, 2, 4, 6. 1, 2, 3, 6, 9. 0, 0, 1, 2, 3. Now we have 3 root vectors. Okay. Now 3 root vectors, they at most span a dimensional 3 space. So the root vector can at most span dimensional 3 vector space. So the rank is at most 3. But then we want to see if the vectors is linearly independent or not. So we do rule operations. Remember, rule operation does not change. Is invertible, so it does not change whether they are linearly independent or not. So we let r negative r1 plus r2. Then what we get is, so r1 is fixed. R2 you get a 0, 0, 1, 2, 3. Okay, 0, 0, 1, 2, 3. And then you subtract. So 1, 2, 3, 1, 2, 3. You do negative R2 plus R3. Replace R3. So you see we have 1, 2, 2, 4, 6, 0, 0, 1, 2, 3, 0, 0, 0, 0, 0. Okay. So this kind of thing. So you see, essentially we have only 2 linearly independent vectors. Okay. So we have 2 linearly independent vectors. So we have 2 non-zero linear vectors. So these root vectors, now the new root vectors, R1, R2, any non-zero linear combination, you cannot get a 0 because here, if you look at the first 2 entries, okay, the root 1 has non-zero entry, root 2 has 0 entries, okay? So any linear combination, you cannot get a 0. Any non-zero linear combination, you cannot get a 0. Okay, so this means the first 2 rules are linearly independent. Okay, linearly independent. Linearly independent. We have exactly 2 linearly independent root vectors. So this actually, we know that rank A in this case is 2. Okay, rank A. Now the null space, the column number is 3. So the null space, dimension of the null space, in this case, it should be 3 because column number is 5. Next time we will compute what is the null space for this example is, and check this indeed it spans a 3-dimensional space. Okay, i.e. the rule, the null space is exactly has dimension 3. Okay, let me stop here for today and continue next week.